Welcome to today's deep dive. If you're joining us, you are likely the kind of person who doesn't just want to know what happened, but exactly how it happened.
Right.
Whether you're using this time to catch up on the cutting edge of physical cosmology or prepping your brain for complex problem solving, or, you just have this insatiable curiosity about our place in the cosmos,
Yeah.
you are exactly where you need to be.
Absolutely.
Today, our mission is to understand how humanity maps the completely unmappable. We are doing a deep dive into simulating the universe, specifically looking inside the Illustris Project and the supercomputers mapping cosmic evolution.
It's a massive topic.
It really is. We're going to unpack dark matter, dark energy, galaxy formation, and try to wrap our heads around how scientists have managed to simulate the entire history of the universe, all 13.8 billion years of it, inside a machine.
And we are using the detailed source material on the Illustris Project as our roadmap today. It is truly a monumental achievement in astrophysics. Over the course of this deep dive, we're going to break down the timeline, the staggering computing power required to pull this off, the underlying physics encoded into the software, and the highly specialized spin-off projects that this original simulation spawned.
Yeah, projects like Illustris TNG and AREPO, which are just fascinating.
Exactly. What makes this so compelling is that it represents a massive paradigm shift in how we do science. I mean, for centuries, astronomy was purely observational.
You just look up.
Right? You build a bigger telescope, you look up, and you try to deduce the rules of the universe based on what you see. But the Illustris Project flips that entirely. It is experimental computational astronomy.
Okay, let's unpack this methodology. Imagine trying to bake a cake, right?
Yeah.
But the recipe takes 13.8 billion years. It requires 25 terabytes of RAM. And the ingredients are things like dark matter and supermassive black holes.
That is a very stressful baking show.
Right. But instead of looking up at the finished product, the finished cake, you start with the raw ingredients and the laws of physics, put them in a digital box, and see if you can bake a universe that actually matches what we see through the telescopes.
Exactly. And the underlying goal isn't just to make a visually stunning digital planetarium. This is about establishing a rigorous, predictive theory of galaxy formation. By building a comprehensive physical model and running it forward, researchers are testing our fundamental understanding of reality.
They want to see if the math actually works.
Precisely. They want to know if the physics we think govern dark matter, dark energy, and standard matter are actually correct when applied on a cosmic timescale.
Okay, but on the surface, that almost sounds circular. Let me play devil's advocate for a second here.
Go for it.
If these scientists, specifically key figures mentioned in our source, like Mark Vogelsberger at MIT and Volker Springel at the Max Planck Institute for Astrophysics, if they are writing the code and they are programming the simulation using the physics rules they already believe are true, aren't they just building a massive echo chamber?
That's a really common critique.
I mean, aren't they guaranteed to just get a universe that perfectly matches their preconceptions?
That is the exact trap they had to avoid. And it's a brilliant question because it strikes at the heart of why this simulation is so incredibly difficult. The way they avoid the echo chamber is by strictly separating the micro rules from the macro results.
Meaning they don't program a galaxy to look like a galaxy.
Precisely. They do not write a single line of code that says, make a spiral galaxy here or make an elliptical galaxy there. They only program the foundational microscopic rules of physics.
Like gravity.
Right. They code in the gravitational constant. They code the thermodynamic properties of gas. They code the rate at which gas cools and condenses to form stars. They drop in dark matter and dark energy based on the parameters measured by the cosmic microwave background.
The echo of the Big Bang?
Exactly. They set up these initial basic conditions as they existed right after the Big Bang, hit run, and let 13.8 billion years of virtual time unfold.
So the macroscopic structures, the massive spiraling galaxies, the galaxy clusters, the cosmic web, all of that has to emerge entirely on its own, organically, just from the micro rules interacting over time.
It's called emergent complexity. If they run the simulation and the resulting virtual universe is filled with galaxies that are way too massive or galaxies that don't cluster together the way real ones do, they don't tweak the galaxies.
Because that would be cheating.
Right. They realize that their understanding of the fundamental microphysics must be flawed. It serves as an unforgiving reality check. If the virtual universe doesn't mirror the observable universe, it means our textbook theories need adjusting.
That makes perfect sense. The simulation is a stress test for our physics. Which brings us to the actual ingredients they put into this digital box. When you are simulating physical cosmology, you can't just throw in some gravity and a bunch of stars and call it a day.
No, the universe is much messier than that.
It really is. The simulation has to include the chaotic stuff. We're talking about star formation, supernova explosions, the formation of supermassive black holes, and of course, the invisible scaffolding of the universe, dark matter and dark energy.
Out of all those ingredients, the one that often surprises people the most is the role of supermassive black holes and supernovae. If we want to understand how a galaxy forms, we have to understand a concept called feedback.
Feedback, because
Yeah.
when we picture gravity, we usually just picture things falling inward. Gravity pulls matter together, so if a universe only had gravity, you'd eventually just get incredibly dense, dead clumps of matter. Everything would just collapse into itself. There has to be a push to counteract that pull.
That push is the feedback, and it is arguably the most difficult thing to model correctly in a universe simulation. Let's look at supernovae first. When a massive star reaches the end of its life, it doesn't just quietly wink out.
It explodes.
It detonates in a supernova, one of those violent explosions in the universe. This explosion sends shockwaves out into the surrounding interstellar gas, heating it up and literally blowing it away.
And since stars form from cold, dense gas, if a supernova blows all that gas away and heats it up, it's effectively shutting off the assembly line for new stars in that area.
Exactly. It regulates star formation. Without supernova feedback, galaxies and simulations convert their gas into stars way too fast.
They burn out.
They do, resulting in virtual galaxies that are unnaturally bright and overly packed with stars compared to the real universe. So the simulation has to constantly track where massive stars are forming, calculate when they die, and model the subsequent thermal and kinetic energy injected back into the gas.
And then you scale that up to the absolute extreme with supermassive black holes. We usually think of black holes as these ultimate cosmic vacuum cleaners that just eat everything. But the reality of a feeding black hole is profoundly explosive, isn't it?
It is. When gas falls toward a supermassive black hole at the center of a galaxy, it forms an accretion disk. This material swirls inward at a significant fraction of the speed of light.
The friction there must be insane.
It's incomprehensible. The friction and magnetic forces within this disk generate massive amounts of heat and radiation. Furthermore, complex magnetic interactions can channel some of that infalling material into massive twin jets that blast outward into space.
So while a black hole is consuming some matter, it's violently ejecting vast amounts of energy outward. The source calls this active galactic nucleus, or AGN, feedback.
Correct. And AGN feedback is crucial for regulating the largest galaxies. Without supermassive black holes actively pushing back against the crushing weight of gravity, the largest galaxies in the universe would continue to grow out of control, becoming vastly larger than anything we actually observe.
They would just eat everything around them.
Right. The Illustris Project had to encode the mathematics of this energetic feedback, the push and pull, the expanding and contracting, to create the delicate, chaotic balance that allows beautiful, intricate structures to form and stabilize over billions of years.
It's basically a cosmic ecosystem.
Yeah.
The predators, the black holes, and supernovae keep the population of stars in check, so the galaxy as a whole can survive and evolve naturally. But simulating an ecosystem of that scale, tracking the gravity of dark matter, the expansion driven by dark energy, the fluid dynamics of gas, and the localized explosions of supernovae over 13.8 billion years. That requires a machine that borders on science fiction.
It requires computational brawn that most people have a hard time conceptualizing. You cannot do modern physical cosmology on a standard computer.
Definitely not.
The Illustris simulation relied on top-tier supercomputers. Specifically, the source mentions the Curie supercomputer located at the CEA in France and the SuperMUC supercomputer at the Leibniz Computing Center in Germany.
Let's put some numbers to this because the scale is just phenomenal. To run the main Illustris simulation, it took 19 million CPU hours. They used 8,192 CPU cores running in parallel. And the peak memory usage during this run hit 25 terabytes of RAM.
That is a staggering amount of memory.
Just to translate that for you listening, if you tried to run this exact simulation on a single high-end desktop processor, you would be waiting over 2,000 years for the progress bar to reach 100%.
And that 2,000-year figure assumes your machine doesn't crash, overheat, or experience a hardware failure, which is a major logistical hurdle when dealing with compute times of this magnitude. When you are running a simulation across 8,192 cores for months on end, the physical reality of the hardware becomes a factor.
Right, computers get hot.
Exactly. Processors generate heat, they require massive cooling infrastructure, individual nodes can fail. The software has to be robust enough to handle the sheer physical strain it puts on the data center.
But the real magic trick is how you get 8,192 separate computer brains to perfectly collaborate on a single universe without stepping on each other's toes. I know in supercomputing, you can't just divide a task easily if everything is connected. If a supernova explodes in processor number 500, the shock wave is eventually going to hit the gas being calculated by processor number 600. They have to communicate instantly.
This is where the MPI approach comes in. MPI stands for Message Passing Interface. It is a standardized means of exchanging messages between multiple computers running a parallel program across distributed memory. Imagine 8,192 cartographers, all standing shoulder to shoulder, each tasked with drawing a small piece of a massive dynamic map.
And the map is constantly changing.
Right, so cartographer A needs to constantly tell cartographer B, hey, a mass of hot gas just crossed the border from my section into yours. MPI is the highly optimized language and protocol they use to shout these updates to each other millions of times a second.
That sounds chaotic.
It would be, without the interface. Minimizing the latency, the delay in that communication is critical. If one core gets bogged down calculating a particularly complex galaxy collision, the other 8,191 cores might have to sit idle waiting for it to catch up, wasting precious compute time.
So the software has to be incredibly smart about how it distributes the workload, ensuring no single processor becomes a bottleneck. Which brings us to the brains of the operation, the actual code running on those machines. The program used for Illustris was written by Volker Springel, and it's called AREPO.
Springel had previously authored a widely used astrophysics code called Gauge-Jidaro, but AREPO represented a monumental leap forward in how we simulate fluid dynamics in space.
Before we get into the heavy math of AREPO, I just have to mention a fantastic piece of trivia from the source. The name AREPO isn't an acronym. It's actually derived from the software square, which is an ancient Latin palindrome.
Yes, the word square.
It's a square containing 5 words: Sator, AREPO, Tenet, Opera, Rotus, that reads the same, top to bottom to top, left to right, and right to left. It's been found in ruins all over the Roman Empire, from Pompeii to Britain. I just love the juxtaposition there. You have the most advanced, bleeding-edge astrophysics code in human history, built to unravel the mysteries of dark matter, and it's named after a 2,000-year-old linguistic puzzle.
It's a wonderful nod to the enduring human desire to find patterns and structure in the universe. And structure is exactly what the AREPO code is designed to handle. At its core, AREPO is built to solve the coupled equations of gravity and hydrodynamics.
We talked briefly about gravity, but hydrodynamics is where this gets incredibly complex. When we look up at the night sky, we tend to think of space as a vacuum, entirely empty except for solid planets and burning stars. But that's not accurate, is it?
Not at all. The space between stars, and especially the space between galaxies, is filled with a diffuse medium of gas, primarily hydrogen and helium. Over cosmic timescales and vast distances, this gas doesn't act like isolated particles. It acts like a fluid.
Like an ocean.
Very much like that. It flows in massive cosmic winds, it pools in gravitational wells, it creates eddies and shock waves. Hydrodynamics is the study of fluids in motion. To simulate a universe, you must accurately simulate fluid dynamics on a galactic scale.
And simulating fluids is notoriously difficult. Anyone who has ever watched an older video game struggle to make water look realistic knows that calculating how a liquid or gas moves and interacts with itself takes massive processing power.
Now imagine simulating a fluid that spans billions of light years, where its density can vary by factors of millions depending on whether it's in the deep void of space or inside a collapsing star-forming cloud.
So how does AREPO do it? The text mentions a highly specific mathematical technique called a moving Voronoi tessellation. This sounds intimidating, but it is actually a beautiful concept once you visualize it.
Let's break it down, because this is really the secret sauce of the Illustris simulation. Historically, cosmologists used 2 different methods to simulate fluids. The first is an Eulerian approach, which involves throwing a fixed, rigid 3D grid over the universe. Imagine a giant cosmic jungle gym. You calculate how much gas moves in and out of each square box in the grid.
The problem with a fixed grid, I imagine, is resolution. The universe is mostly empty space. If your grid boxes are too big, you can't see the fine details of a galaxy forming. But if you make the boxes small enough to see a galaxy, you suddenly have trillions of empty boxes in the cosmic voids that your computer is wasting time calculating for no reason.
Exactly. It's incredibly inefficient. You are burning CPU hours calculating nothing. The alternative method historically used was Lagrangian. specifically smoothed particle hydrodynamics, or SPH. In this method, there is no grid. Instead, you represent the gas as millions of individual virtual particles, and you track where they move. This is great because your computing power naturally follows the matter.
But I'm guessing SPH has its own drawbacks.
It does. It struggles with fluid instabilities and sharp shock waves. When two gas clouds smash into each other, SPH sometimes artificially smooths out the collision, losing the chaotic, turbulent details that are essential for mixing the gas.
So a fixed grid is bad at following the matter, and floating particles are bad at capturing sharp fluid dynamics. Volker-Springel needed a third way, and that is the moving Voronoi tessellation.
Right. A Voronoi diagram is a way of dividing space into distinct regions based on distance to a specific set of points. The classic example is mapping cell phone towers.
Okay, I can picture that.
If you put 100 cell towers on a map, a Voronoi diagram draws boundaries around each tower, creating a polygon. Everywhere inside a specific polygon is closer to that tower than to any other tower.
Okay, so take that flat map of cell towers, make it three-dimensional, and apply it to the universe.
Exactly. AREPO casts a brilliant mathematical net of these 3D Voronoi cells over the entire virtual universe. But here's the genius part. The net is not rigid. The points that define the cells are allowed to move with the flow of the cosmic gas.
Oh, wow. So as gravity pulls gas together to form a galaxy, the cells of this mathematical net flow inward alongside the gas, shrinking and clustering tightly together where the density is highest.
Exactly. It's an adaptive dynamic mesh. In the empty voids of space, the cells stretch out and become enormous, saving computing power. But in the dense, turbulent center of a forming galaxy, the cells become incredibly tiny and numerous, providing ultra-high resolution right where the physics are most complex.
That is so smart.
And because it's still technically a mesh, it handles fluid dynamics, turbulence, and shockwaves beautifully. The moving Voronoi tessellation gave AREPO the best of both historical methods without the fatal drawbacks of either.
It is an elegant, dynamic solution to mapping the unmappable. It allows the simulation to breathe, contracting its focus where the action is and expanding where space is empty. They took this code, fired up the supercomputers, and let it run for 19 million CPU hours. They built a 13.8 billion year universe. And then they did something that I think defines the best of modern science. They gave the universe away.
The commitment to open science here is remarkable. In April 2015, just 11 months after the foundational papers describing the Illustris results were published, the project team publicly released the data products from all their simulations.
They didn't lock it behind a paywall.
No, and they didn't hoard it for their own institution's exclusive use.
We need to quantify what giving away a universe looks like. We are talking about over 230 terabytes of cumulative data volume. During the simulation run, they couldn't just save a single video file of the whole thing. Instead, they took full snapshot particle data at 135 distinct time points throughout the 13.8 billion years, plus one final snapshot, making a total of 136 snapshots.
Think of it like a time-lapse of the cosmos. These snapshots contain the precise location, velocity, mass, and temperature of billions of resolution elements at that exact moment in cosmic history.
But raw data of billions of particles isn't incredibly useful on its own. It's just a wall of numbers. The team went a step further and processed this data into usable tools for the wider astronomical community. They included things called group catalogs of individual halos and subhalos. For you listening who might not know, what exactly is a halo in this context?
In cosmology, a halo refers to a massive clump of dark matter. Dark matter doesn't interact with light, but it has mass, so it exerts gravity. In the early universe, dark matter clumped together into these vast, invisible halos. The gravity of these dark matter halos is what pulled in the normal gas and dust, eventually sparking star formation.
So the dark matter halo is the invisible bowl, and the galaxy is the soup that collects inside it.
That's a great way to visualize it. So a halo is the main dark matter structure, and a subhalo is a smaller clump of dark matter residing within it, which usually corresponds to a single galaxy or a satellite galaxy. By releasing these group catalogs, the Illustris team basically provided a full census of every single dark matter bowl and every single galaxy soup in their virtual universe, categorized by mass, size, and star formation rate.
And they also included merger trees. I love this concept. A merger tree is exactly what it sounds like. It's a genealogical family tree for galaxies.
Galaxies don't usually form in isolation. The hierarchical model of structure formation dictates that small things merge together to form bigger things. Small clumps of dark matter and early stars smash together to form dwarf galaxies. Those dwarf galaxies get pulled together by gravity and merge into massive spiral galaxies like our Milky Way.
And eventually, spiral galaxies can collide to form giant elliptical galaxies.
Precisely. A merger tree allows a scientist to pick a massive galaxy in snapshot 135 of the present day and trace its ancestry backward through time. They can see exactly which smaller galaxies collided, when they collided, and how those collisions triggered bursts of star formation or fed the central black hole. It's tracing the lineage of a cosmic structure over billions of years.
And the accessibility of this data is a game changer. Releasing 230 terabytes of data is one thing, but expecting researchers around the world to have the local storage and computing power to download and analyze it is unrealistic. So the Illustris team built a web-based API and application programming interface.
Which effectively means you don't need a supercomputer in Germany to study this universe. A graduate student with a standard laptop in a developing country, or a researcher at a small university without a massive funding grant, can write a script, connect to the API via the internet, run a specific search query directly on the Illustris servers, and download just the specific subset of data they need.
It entirely democratizes the cosmos. It allows thousands of researchers to test their own unique hypotheses about galaxy rotation, black hole growth, or dark matter distribution against a state-of-the-art simulation. It accelerates the pace of discovery across the entire field because the bottleneck of access has been removed.
It's a beautiful model for how science should be shared.
Now, we've been deep in the weeds of APIs, terabytes of RAM, and supercomputing architecture, but I want to pivot to something that highlights the broader cultural impact of this achievement. In December 2018, the Illustris simulation received a very unique honor from a surprisingly old-school institution. The German Postal Service recognized the project with a special series postage stamp.
It is a wonderful, almost poetic contrast. On one hand, you have 230 terabytes of the most complex, dynamically generated digital information ever produced by humanity. And on the other hand, it is commemorated by being printed on a tiny, physical square of paper that you lick and stick on a letter.
I think it speaks volumes about how scientific milestones transcend academia. When a physics simulation gets put on a postage stamp, it means it has entered the cultural zeitgeist. It's a physical stamp of approval for a purely virtual universe. And I think a huge part of why it captured the public imagination is the visual aspect. The data visualizations generated by Illustris are absolutely breathtaking.
They really are. When you render the gas density, temperature, and metallicity of the Illustris universe, it looks incredibly authentic. You see the glowing, delicate filaments of the cosmic web connecting massive glowing nodes of galaxy clusters. You see the distinct spiral arms of virtual galaxies rendered in vibrant colors that map to real physical properties.
It bridges the gap between abstract math and human intuition. When people can literally see the output of AREPO's hydrodynamics, it makes the staggering complexity of physical cosmology feel tangible.
But the scientific process doesn't stop at a successful proof of concept or a commemorative stamp. The original Illustris simulation was a triumph, but it wasn't perfect.
Right, there were flaws.
There were discrepancies between the simulated universe and the real one. Certain populations of galaxies didn't match perfectly, and the physics of black hole feedback needed refinement.
Which is exactly how science is supposed to work. You build a tool, you push it to its absolute limits to see where it breaks, and then you build a better tool. Once they proved that the AREPO code could construct a universe, the team didn't just pat themselves on the back and move on. They initiated a series of highly specialized, incredibly ambitious spin-off projects to ask deeper, more complex questions.
If we consider the original Illustris simulation as a broad foundational map of the world, the spin-offs are like using specialized satellite imaging to zoom in on specific topographies, weather patterns, or demographics.
The first and most prominent follow-up was Illustris TNG, which literally stands for the next generation. This project was presented in July 2017, again led by Volker Springel, alongside a broader team of scientists from institutions in Germany and the US.
With TNG, they significantly upgraded the physics programmed into the simulation. The most crucial addition was a field of physics known as magnetohydrodynamics.
And we talked about hydrodynamics, the flow of fluids. Adding the magneto prefix implies we are now tracking magnetic fields. Why is that necessary? Are magnetic fields really that important in the vacuum of space?
They are profoundly important. While space is a vacuum by earthly standards, The diffuse gas that permeates the cosmos is often ionized, meaning the atoms have been stripped of electrons, turning the gas into a plasma. Plasmas are highly conductive and interact strongly with magnetic fields.
So the magnetic fields can actually shape how the gas flows.
Exactly. Magnetic fields can provide pressure that supports gas against gravitational collapse. They influence how cosmic rays travel through a galaxy. And crucially, they play a massive role in how supermassive black holes accrete matter and launch those massive, powerful jets we discussed earlier. In the original Illustris simulation, the fluid dynamics were purely kinetic and thermal. By adding magnetohydrodynamics to Illustris TNG, they made the cosmic fluid vastly more realistic.
But adding magnetic fields to the moving Voronoi tessellation means the mathematical complexity just went through the roof.
It did. Tracking the strength and direction of magnetic fields across billions of moving computational cells requires an immense leap in processing power.
Which explains the hardware upgrade. The flagship simulation of this new project was run on the Hazel Hen machine at the High Performance Computing Center in Stuttgart, Germany. They scaled up from the original 8,192 computer cores to employing up to 25,000 computer cores working in parallel. And, continuing their commitment to open science, they released the TNG data publicly in December 2018. But this time, they made it even more accessible by including a JupyterLab interface.
For listeners who might not be in the computer science field, JupyterLab is a web-based interactive development environment. It allows researchers to write and execute code, like Python, directly in their browser. They can analyze the TNG data right on the project servers without having to download massive datasets or set up complex coding environments locally. It lowered the barrier to entry even further.
Illustris TNG was a massive step forward, but it was still simulating a large, representative volume of the universe. What if you want to understand something very specific, like the exact history of our own home galaxy? That brings us to the first of the highly specialized spin-offs, the AREPO project.
The AREPO project is fascinating because it shifts the focus from the macro to the micro. The source notes that AREPO consists of high-resolution zoom simulations of Milky Way-like dark matter halos.
Break down that term for us. Zoom simulation. Does that mean they just take the data from the main simulation and look really closely at one part?
Not exactly. In a full-box simulation like Illustris, the resolution, the smallest detail you can accurately model, is limited by the sheer size of the universe you're trying to fit into the computer's memory. If you want to study the fine details of how a galaxy's spiral arms form, or how a galaxy cannibalizes smaller dwarf galaxies over time, the full-box resolution isn't sharp enough.
It's like trying to read a license plate in a satellite photo of an entire continent.
Right. So a zoom simulation uses a clever trick. They run a low-resolution simulation of a large volume of space, and they identify a specific dark matter halo that has roughly the same mass and environment as our Milky Way. Then they rerun the simulation from the Big Bang, but they concentrate almost all of the computing power and millions of high-resolution particles specifically into that one small region of space.
While the rest of the universe surrounding it is simulated at a very low resolution just to provide the correct gravitational background.
Exactly. It allows them to study the incredibly intricate formation history of a Milky Way analog, its spiral structure, its central bulge, its surrounding halo of stars, and breathtaking high definition, helping us understand how our own galactic backyard came to be.
That is brilliant. Okay, moving down the timeline. In 2021, we see the introduction of a spin-off called Thesan. And this one tackles a very specific and frankly mysterious era of cosmic history. The source describes Thesan as a radiative transfer version of Illustris TNG designed to explore the epoch of reionization. I think we need to define some terms here, starting with the epoch of reionization. What is that?
To understand reionization, we have to go back to the cosmic dark ages, roughly 380,000 years after the Big Bang. At that time, the universe had expanded and cooled enough for protons and electrons to combine and form neutral hydrogen atoms.
Which means the universe was no longer a hot, glowing plasma.
Right. It became filled with a thick, opaque fog of neutral hydrogen gas. There were no stars, no galaxies, no sources of light. Hence the Dark Ages. But eventually, gravity pulled enough gas together to ignite the very first stars and the first primitive galaxies.
And when those stars turned on, they started pumping out ultraviolet radiation.
Yes. And those high-energy UV photons slammed into the surrounding neutral hydrogen fog, tearing the electrons away from the protons. This process is called ionization. As more stars formed, these bubbles of ionized transparent gas grew and merged, until eventually the entire universe was reionized. It was the dawn of light, The fog lifted, and the universe became transparent to light, which is why we can see distant galaxies today.
That is an incredibly poetic moment in the history of the cosmos. But simulating it requires a new type of physics, which the text calls radiative transfer.
Tracking the gravity and fluid dynamics of the gas is hard enough. Radiative transfer requires calculating how individual packets of light photons travel through that moving fluid, how they are absorbed by the gas, and how that absorption heats and ionizes the gas, which in turn changes the pressure and the fluid dynamics. It's a deeply complex feedback loop between light and matter. Thiessen was built specifically to model this dawn of light and understand how the first stars transformed the entire universe.
From the dawn of light, we move to the absolute giants of the cosmos. In 2022, the Millennium TNG project was launched. The text notes that it employs the galaxy formation model in a larger cosmological volume to explore the massive end of the halo mass function for detailed cosmological probe forecasts. There's a lot of dense terminology there.
Okay.
Let's start with the halo mass function.
Simply put, the halo mass function is a demographic census of the universe. It is a mathematical curve that tells you how many dark matter halos exist at various different masses.
So it tells you that there are trillions of small halos, billions of medium halos, and only a few massive ones.
Correct. But to accurately plot the massive end of that curve to study the absolute largest dark matter structures in the universe, you run into a statistical problem. Because massive halos are extremely rare, you won't find many of them in a small or even medium-sized simulation box.
If you want to study the demographics of billionaires, surveying a small town won't work. You have to survey an entire country.
Perfect analogy. Millennium TNG scaled up the volume of the simulation drastically. They needed an enormous virtual universe to ensure they captured a statistically significant sample of these extremely rare, gigantic structures. They want to understand how these titans form and how they cluster, because the exact number of these massive halos is highly sensitive to the fundamental properties of dark energy and the total mass of neutrinos. By comparing the massive end of the halo mass function in the simulation to what telescopes like Euclid or the Nancy Grace Roman Space Telescope will observe, scientists can precisely calibrate our cosmological models.
And that scales perfectly into the final spin-off mentioned, TNG cluster, introduced in 2023. This is a suite of high-resolution zoom-in simulations specifically targeting galaxy clusters.
If Millennium TNG was casting a wide net to find where the giants live, TNG clusters are putting those giants under a microscope. Galaxy clusters are the largest gravitationally bound objects in the universe. We are talking about structures containing hundreds or even thousands of individual galaxies, all swarming around inside a colossal dark matter halo permeated by incredibly hot X-ray emitting gas.
The physics in an environment like that must be incredibly extreme. You have galaxies moving at millions of miles an hour, smashing into each other, being stripped of their gas by the sheer friction of moving through the cluster environment.
It is the ultimate cosmic mosh pit. TNG cluster uses the zoom technique we discussed earlier to resolve the violent, complex astrophysics happening inside these massive clusters. How does a supermassive black hole in the central galaxy of a cluster manage to heat up gas that is millions of light years away? How do galaxies survive plunging through the center of the cluster? These are the frontier questions of astrophysics today.
So let's pull all of this together. We started with the desire to map the unmappable. We looked at a single, mathematically elegant piece of code called AREPO, named after a Roman palindrome. From that foundation, teams of brilliant scientists utilizing tens of thousands of supercomputer cores, millions of CPU hours, and an incredible grasp of gravity, hydrodynamics, and magnetic fields managed to simulate a 13.8 billion year universe.
They simulated the invisible scaffolding of dark matter, the chaotic explosions of supernovae, the terrifying feedback of supermassive black holes, the intricate dance of fluid dynamics, the dawn of light during reionization, and the assembly of the largest clusters in the cosmos.
And then, instead of locking it away, they opened the doors. They provided APIs and web interfaces, handing a 230 terabyte digital universe to the global scientific community. It sparked a golden age of computational cosmology, earning a place in cultural history right down to a commemorative postage stamp.
The Illustris Project and its TNG successors are more than just a map of stars. They are a testament to human ingenuity. By combining the complex math of microphysics, they created a sandbox for reality. They built an environment where we can test the very laws of nature and watch the consequences unfold in fast forward.
And for you listening to this, whether you are trying to conceptualize the vast cosmic web or you are just looking for a bit of profound inspiration before you tackle your next big project, the ultimate takeaway here is the astonishing power of modeling complex systems. Think about the implications. If human beings can collaborate, write code, and build machines powerful enough to simulate 13.8 billion years of galaxy formation down to the magnetic fields and the cooling rates of gas, what other massively complex, seemingly unsolvable problems can we model, understand, and ultimately solve here on Earth?
It is a deeply empowering thought. But in the spirit of this deep dive, I want to leave you with an idea that is perhaps slightly more provocative to mull over. We've discussed the unbelievable detail of the Illustris simulation. It is so complex that researchers require merger trees just to track the billions of virtual cosmic events and genealogies over vast stretches of time. It is, for all intents and purposes, a functioning universe within a machine.
A universe constrained by 25 terabytes of RAM.
Indeed. But consider the trajectory of our technology. If a supercomputer in Germany in the 21st century can generate 136 distinct time snapshots of a virtual reality that remarkably mirrors our own observable universe, what happens in 1,000 years or 1,000,000 years? If we can simulate reality this well now, how do we know for certain that our own universe, with all its galaxies, dark matter, and cosmic webs, isn't just the ultimate, infinitely high-resolution simulation running on some unimaginable cosmic supercomputer?
Oh, that is the perfect, mind-bending thought to end on. A reality check for reality itself. Thank you so much for joining us on this deep dive into the Illustris Project and the incredible science of simulating the cosmos. Keep asking questions, keep wondering at the scale of it all, and we will catch you on the next one.